In the last few videos, we've been taking a look at energy, and specifically been looking at energy transfers with macroscopic objects. And in those cases, we've seen, especially when dissipative forces were involved, that sometimes energy would be transferred to a microscopic level, and we wrote that off as being a heat transfer to increase thermal energy and promised that we would get to that later. Well, here we are, and looking at energy transfers on a more microscopic level is a field known as thermodynamics. And we will start with, as a segue here, with the experiment due to Joule, who later had the unit of energy named in his honor for this work, for what's usually called the mechanical equivalent of heat. So the idea of the experiment goes like this. Joule stuck a thermometer in some beaker of water, and we know that you can heat up a beaker of water, so this is supposed to be a flame, with a Bunsen burner or something like that. We know that we would be transferring heat in, and we'll define that idea more thoroughly in a bit. And as a result, though, the temperature would go up. That was measured in the thermometer. So Joule did another experiment, though, where he took the same beaker of water with the same thermometer, but now instead of putting a Bunsen burner underneath, he stuck sort of a paddle wheel-like contraption into the water, like so. And he tied this on to a system of pulleys, hung a weight over the side, and he rigged it up so that this would fall at a constant speed. So you'd end up getting, as a result, the paddle wheel contraption is spinning around in the water. Since this was rigged up very carefully to have the weight fall at a constant speed, the potential energy is decreasing, but there's no increase in kinetic energy. The only place the energy can be going is into the water. And sure enough, it turned out that the temperature of the water was also increasing. So nowadays, we would interpret the temperature of the water as being related to the average kinetic energy of the water molecules, and in fact, the current official definition of temperature is based on that, but it'll take me a few series of videos to get to that point. But in the early days of work on thermodynamics, people weren't entirely sure that this heat transfer from the flame was the same kind of thing as Joule's mechanical contraption. It turns out it is. But they didn't know at the time, and so they're very careful, and they called it the mechanical equivalent of heat. They're saying, yeah, okay, Joule has shown that you can do mechanical work on the water and cause the temperature to increase in exactly the same way that running a Bunsen burner under the beaker would cause the temperature to increase. Now, because it took quite a while to figure out that heat transfers were indeed transfers of energy, this leaves us with a sort of a mishmash of units dealing with this stuff. So if you've seen any kind of thermodynamics in a previous course or something like that, say chemistry or something like that, you've probably run into the calorie. This is the heat required to raise 1 gram of water by 1 Celsius degree. It turns out that this is equal to 1.484 joules. So if you do 4.184 joules of work on 1 gram of water, you'll also raise its temperature by 1 degree. And so we now understand the calorie to be a unit of energy, and this is the equivalence. Now, just a side note here. If you look at the nutrition facts label on some food, you'll see that they'll use a capital C here. This is called a great calorie or a food calorie. In a lot of countries, they will do us a favor and actually just write kcal like this to make it less confusing. But that turns out to be 1,000 of these small c calories, or 4,184 joules, no decimal point. So you got to be a little careful about that if you're dealing with situations that involve food. If there's a capital C in the calorie, that's one of these food calories. That's 1,000 of the 1 gram, 1 degree calories. Okay, so we've talked about doing work on water and causing the temperature of the water to go up. And we talked about measuring that temperature with a thermometer. And this is as good of a segue as anything into an initial operational definition of temperature. We will refine this multiple times. I'm taking sort of a quasi-historic approach here, but at a first pass, we could say that temperature is that thing measured by a thermometer. Now, you know that when you look at a thermometer, it's calibrated in degrees and all that. We call that a temperature scale. And just pause and ponder for a moment and ask yourself, what is the point of having a temperature scale? Okay. And the main point is just to foster communication. It doesn't matter what the scale is, as long as it's agreed to. So, for instance, if you see a weather report and it says that's 30 degrees outside, in almost the whole world, you'll be saying, okay, probably some lighter weight clothes, t-shirt, something like that. That'd probably be a good choice. On the other hand, if you happen to be in, say, the United States or a couple of other countries, you would look at that and say, probably want to get out, start thinking about getting out the winter jacket, or at least maybe, put a layer underneath the sweatshirt, something like that. And the point is, in the first example, that was 30 degrees Celsius. The second example, it was 30 degrees Fahrenheit. And from a communications perspective, it doesn't matter which one you choose, as long as everyone knows what you're talking about. You can go and look at the weather report and decide how you want to dress. So to that point, let's see how you would go about constructing what we call a common temperature scale. And then we'll refine these definitions a few times along the way. So we'll start with the Celsius scale, mostly because it's in the widest use in the scientific community and, frankly, most of the world. So you go ahead, you take your thermometer, and to calibrate it, what you do is you first stick it in some known cold temperature. It often gets called the ice point, but doesn't have to have anything to do with ice, but for a traditional common temperature scale, you might say stick this in ice water solution, or ice and water in a beaker or something like that. Stick the thermometer in and wait for the level to stabilize. And when you do that, you assign it some value, let's say 0 degrees C in the Celsius system. Okay, and then you go ahead and repeat this process by, say, sticking in boiling water where the liquid and gaseous phases of water simultaneously exist. So this gets called the boiling point, but again, for calibration purposes, it doesn't have to be something boiling. It's just convenient from a lab perspective. And you give it a name like, let's say, 100 degrees C. Something like that. All right. Now, by comparison, just to show that there's nothing particularly special about doing this with in Celsius, let's do this in Fahrenheit. Oops. And let me slide that back there. There we go. So now let's calibrate a Fahrenheit thermometer. Again, it's the same process. You're just giving a different name to the ice point. Instead of calling it 0 degrees, you call it 32. And instead of calling it 100 degrees, you call it 212. Now these numbers might seem a little odd to you. So you might wonder what you'd think that Fahrenheit, when he came up with this scale, probably had some convenient numbers in mind to be, say, 0 and 100. And you would be correct. It turns out that 0 degrees Fahrenheit corresponded with the coldest day he ever measured in his particular part of France. You can already see that there's a bit of a reproducibility issue, because this means that you'd have to bring your thermometer over to where his thermometer is and sit and wait for another record cold spell to come around, and then compare the height of the mercury in your thermometer to the mercury in his thermometer. And similarly, the original definition of 100 was a little fraught with technical difficulties too. It was the temperature of the blood of a freshly slaughtered chicken. And of course you can see there, did the chicken recently lay an egg? That would probably have that might have an effect on the temperature. Is the chicken fighting off some sort of chicken cold or something like that? That would probably have an effect on the temperature of the chicken. How fast did you get the blood drained out? You can see there's a lot of technical issues here. And so it turned out that neither of these points in the original scale were very good for calibration. So, but people did notice that on his original thermometer that water froze at almost 32 and it boiled at almost 212. So they just kind of rejiggered the scale a little bit to say that water freezes at 32 and boils at 212. So just slightly off from the original coldest day and freshly slaughtered chicken definition, but certainly a lot easier to do in a lab. Now here I'm going to get a little pedantic about notation because I think it's useful. And a lot of books are starting to sidestep this a bit. It does matter where you put the degree sign relative to the scale indicator. So if the degree sign comes before, say, the letter C or the letter F, that refers to the actual reading on the thermometer. Now, if you take a difference of two temperatures, like let's say you want to know what the difference in between the boiling and the ice point in the Fahrenheit scale is, you would say, okay, that's 212 minus 32 is equal to 180 Fahrenheit degrees. So if the degree sign comes after the letter F, that would be a temperature difference. So if it comes before the letter F, that's a reading. Before the letter F, that's a difference. Similarly here, although maybe a little less obvious, 100 minus 0 is going to give me 100 Celsius degrees. And that's going to be my temperature difference between the boiling and the ice point in the Celsius system. So again, degree sign before means I read 100 on the thermometer. 0 means I read 0 on the thermometer. 100 here means I took the difference of these two readings, which happen to be 100 minus 0. So here's maybe a little easier to see that how that works out here in Fahrenheit, where you're saying 212 minus 32 is 180 Fahrenheit degrees. So again, 212, I read it on the thermometer. 32 degrees F, I read it on the thermometer. 180 F degrees, I took the difference of two readings. So that's how to interpret a degree sign before or after. And I find it very useful when trying to keep things straight. It's starting to fall out of fashion a bit, and a lot of this has to do with the definition of the Kelvin, which we'll get to when we get to absolute temperature scales in a little bit. And so a lot of books are soft pedaling that, but I think it's still a very useful thing to keep straight. So let's say you need to convert between the two scales. Probably the easiest to convert before is to just think about converting temperature differences. So this is the difference in two readings on a particular scale. We'll then talk about converting readings and what all we need to do to adjust for that. So here we go and take a look. So let's say you have a Celsius temperature difference, and you want to get the corresponding Fahrenheit temperature difference. The thing you need to adjust for is the size of the degree. In Celsius, there's 100 Celsius degrees, and in Fahrenheit, there's 180 in the same range. 180 to 100 is a 9/5 ratio. So this means for every 5 Celsius degrees, there are 9 Fahrenheit degrees. So if I take my temperature difference in Celsius and multiply that by 9/5, that takes into account the fact that the Fahrenheit scale is more finely divided, and there are 9 Fahrenheit degrees per 5 Celsius degrees to give us a Fahrenheit temperature difference. And if I need to go the other way around, I can just invert that. There we go. So if I have a Fahrenheit Fahrenheit temperature difference, and I want to convert that into the corresponding Celsius temperature difference, I would just multiply by 5/9. Now, where things get a little confusing is if you need to convert temperature readings. So this is the actual number that you're reading on the thermometer. So we'll start with, let's say you have a Celsius temperature, and we want to get the corresponding Fahrenheit temperature. So there's going to be a 3-step process. The first step is to find a common reference point to work off of. In the usual equations that you see in books, a common reference point that gets used is the ice point. So what you do is you first figure out how many degrees different you are than the ice point. So you would take the Celsius temperature that you've got and you would subtract 0. Nobody ever bothers writing the -0 part, but that's what you're doing. You subtract 0 in order to get the temperature reading. So the temperature difference. So the temperature reading in Celsius is numerically always the temperature difference against the ice point. The next step is you would take that now temperature difference and times that by 9/5. Let me put in the -0 just to make that obvious there for a moment. You would times that by 9/5 to account for the size of the degree. And so you now have the corresponding temperature difference off of freezing in the Fahrenheit system. However, you have to add 32 to that difference in order to get an actual reading. So we add 32, and there you go. Now, usually nobody ever bothers writing this -0 bit, so you would just say T Fahrenheit equals 9/5 T Celsius plus 32. But the process here is take the temperature, subtract the ice point temperature, get a temperature difference, adjust for the size of the degree, and then add a temperature, add the ice point temperature in the new scale in order to get it to be a reading. Okay. So now let's try that process in the other direction. So let's say you have a Fahrenheit reading and you want to get a Celsius reading. Okay. So the goal here is you want to say T Celsius equals. So again, same process here. You'd look at your thermometer, wherever your reading is, you would subtract 32 in order to get the number of Fahrenheit degrees between the freezing point and the temperature you care about. So this will now be a temperature difference off of freezing, T Fahrenheit minus 32. You would then multiply by 5/9 to adjust for the fact that Celsius degrees are coarser and Fahrenheit degrees are finer. And then you would go and you would add the ice point temperature back in, because now what you have here is the number of Celsius degrees off of the ice point temperature. But in Celsius, the name of the ice point temperature is 0. So again, when you look up the equations in tables or whatever, nobody ever bothers writing the +0 here, and you're left with T Celsius equals 5/9 of the quantity T Fahrenheit minus 32. So that's what you'll find in almost any table anywhere, but hang on, and if you find it hard to remember when exactly you're supposed to add or subtract a 32, I've got a different way to think about it that you may or may not like, but hey, it's worth a shot. So let's just do a couple conversions real quick here to get a feel for this. So let's think about converting 45 Fahrenheit degrees to Celsius degrees. So here, the first thing you want to do is you want to look at where is the degree sign. Well, the degree sign is after the letter, so that means we're converting a difference. So we would use the difference relations. So that would be delta TC equals 5/9 delta TF. So that'd be 5/9 of 45 F degrees gives me 25 C degrees. Now that is going to be different than converting 45 degrees F to degrees C, because here now the degree sign is in front of the letter, so that is going to be a temperature reading. So that means that we need to use the equation for readings. So this would be TC equals 5/9 TF minus 32. So this would be 5/9 of 45 minus 32. This gives us 7.22 degrees C. All right. Now, if you go and look at this, you realize that although in temperatures where most humans voluntarily live, the corresponding number on the Fahrenheit scale will always be bigger than on the matching Celsius number. You realize, though, that since there are more Fahrenheit degrees than there are Celsius degrees, you must get to a point somewhere where the two temperatures are the same, and then which turns out it's going to be in the negative numbers. And then once we get past that point, the Fahrenheit scale will be exploring bigger negative numbers than the Celsius scale. So there is a temperature at which they are equal. So let's figure out what that temperature is. So we can use, let's say, the Fahrenheit to Celsius equation here. So again, we'll start with T Celsius equals 5/9 T Fahrenheit minus 32. But this is at the magic temperature T, where the two are the same. So we can just substitute in a T on both sides. Oops. And then substitute around. So let's see. Multiply through by 9. So this would be 9t if I times both sides by 9. Then let's times this 5 through. This will give me 5t. 5 times 32 is 160. Subtract 5t from both sides. We get 4t equals negative 160, or t equals negative 40. So it turns out that negative 40 is the magic temperature where the two readings will just happen to have the same number. That is also darn cold. Jack London's story to build a fire references this. He talks about a Yukon miner who is out walking and he's trying to figure out how cold it is, and he spits. And he notices that the spit turned into ice before it hit the ground, and so he concludes that the temperature is around negative 40. If the spit made it to the ground and then froze, that would be like maybe about and then froze almost right away, then that would be more like negative 30. But apparently, if it freezes before it hits the ground, it's negative 40, or at least that's how it was told in the story. In any event, it's darn cold. So, but the fact that these two temperatures are the same gives us another way that we could do temperature conversions. So again, let's say you want to convert Fahrenheit to Celsius. All we need is to take a difference off of some temperature that we understand. So let's say here, for our Fahrenheit temperature, since we understand negative 40, let's take the temperature difference off of negative 40. So now this is a difference in F degrees. We multiply by 5/9 to change the size of the degree, and then we add back in the name of that reference temperature, which was negative 40. So doing that, you can say that to go from Fahrenheit to Celsius, that would be 5/9 of the Fahrenheit temperature plus 40, right? Minus and minus is a plus. Minus 40. And you can do the same exact logic going from Celsius to Fahrenheit. The only difference is you have a TC minus a negative 40, and you'd be times by 9/5. So that'll work out to be TC plus 40 minus 40. So I don't know if you like these any better or worse, but if you're having a hard time remembering when you should be adding or subtracting a 32, here's an option where you don't have to think about that. You always take the temperature from the scale you're converting from, add 40. Now, if you're going from Fahrenheit to Celsius, you'll times by 5/9 because Fahrenheit is more finely graduated, so the 9 has to go on the bottom. And then you subtract 40. Or if you're going from Celsius to Fahrenheit, you take the Celsius temperature, add 40. Then you times by 9/5 because with Fahrenheit being the more finely graduated scale, there'll be more Fahrenheit degrees than Celsius degrees, so the 9 needs to be on the top. Then subtract 40. So add 40, multiply by 5/9 if you're going to Celsius, 9/5 if you're going to Fahrenheit, and then subtract 40. I don't know if you like that any better or not, but it's at least a way, if you're having a hard time remembering whether you should be adding or subtracting 32s, here's a way that you can do it where you just always remember add 40, do the thing, then subtract 40. All right, so let's work towards absolute temperatures. And to that end, let's refine our thermometers. A better design of thermometer is instead of a liquid thermometer is what's called a constant volume gas thermometer. So what you do is you have a cell of gas that you want to measure the temperature of, and you run some glassware along, and you put in sort of a funky crook like this. Something like, oops, I need to leave a little gap right at the bottom. Then close it back up at the top. And right here, there will be a little volume, little volume adjustment reservoir, it's called. Okay. And so the idea goes like this. You put a reference mark, you fill this tube with mercury or some other suitable liquid. I don't want people getting mercury poisoning here, and you rig it up so that you either add or remove mercury in the adjustment reservoir until the mercury here is at a reference level. And whatever you do, never pipette by mouth, and especially if it's mercury. Okay, so you add or subtract mercury here until the column of mercury matches this line. And then on the other side over here, you'll have some more mercury here. And the idea is right here, this is evacuated, so the pressure here is basically zero, not counting a few random mercury atoms that happen to be floating around. So what you can do is you can measure this height. Now, the height that you have there, as we'll see a little later, is directly proportional to the pressure of the gas. And by carefully adjusting this so that there's always the same volume of gas in here out to there, if you plot the pressure as a function of temperature for different gases, you start to see something. So here I'm going to plot temperature and pressure. And here this is different gases, different gases and different densities. Although it turns out that once things start getting to be at low pressures, All that really matters. Or sorry, my bad. It turns out that for the most part, as long as you're not at crazy high pressures, the main thing that matters is just being what your density is. So anyway, it turns out that for different gas samples, you can make a plot of the pressure of the gas as a function of temperature. And now what will happen is the gas will either go liquid or sublimate at some point. Before it gets to zero, but it turns out that every single gas extrapolates to a pressure of zero at exactly the same point. And as you get the densities of gas lower and lower and lower, you can push this extrapolation closer to before it freezes or goes liquid. You can get closer and closer to this extrapolation point. So what this is showing us is that there is a lowest temperature. And this lowest temperature turns out to be negative 273.15 degrees C. And this gets called absolute zero. So if it turns out, and the reason is that it doesn't make sense to talk about a negative pressure. When we get into looking at fluids, we'll understand why. But just for now, take it that it doesn't make sense for there to be a negative pressure. And so if everything is extrapolating to zero at the same temperature, that means there is a lowest possible temperature. So if there is a lowest possible temperature, it then makes sense for purposes of doing thermodynamics calculations, but definitely not for living our daily lives, to define what are called absolute temperature scales. So the one in most common use is the Kelvin scale. And no, I did not forget to write a degree sign. I'll get into that in a second. And then let's compare that, say, against the Celsius system. So the two hypothetical points of comparison for setting the scale, the lower point now will be absolute zero. Even though we can't, it turns out, by the third law of thermodynamics, we cannot attain it. We can still we can still always extrapolate out where it would be on our thermometer. And then I'll finesse this point a bit more in a minute, but for purposes of discussion, let's just use the freezing point of water as our upper temperature. So remember, this is 0 degrees C, and this is negative 273.15 degrees C. So here in the Kelvin system, we'll say this is 0 Kelvin, and this is 273.15 Kelvin. So now, the thing I want you to notice here is that the values of the temperature differences are the same. The temperature difference here is going to be 0 minus a negative 273.15. So the delta T in the Celsius system between these two temperatures is 273.15 Celsius degrees. And delta T in the Kelvin system is going to be 273.15 minus 0 is also 273.15 Kelvin. And yes, I did not draw a degree sign. Annoyingly, in the Kelvin system, it used to be that you would write degrees Kelvin and Kelvin degrees. But then eventually the international bodies that decide these things decided, mostly for convenience and typesetting reasons, to just drop writing degree signs altogether. They viewed that it was always clear from context whether you're talking about a reading or a difference. So you're on your own for that one. But anyway, to convert between the systems, if it's a temperature difference, since it's exactly the same number of degrees between the 2 points, the temperature differences are always the same numerically. So C degree is another way of writing Kelvin when you're talking about a difference. Now, if it's a reading, you would take the Celsius temperature and you would add 273.15 to get Kelvin. And so that's degrees C to Kelvin. And again, you don't write a degree K or K degree, unfortunately, although it's useful to keep that in mind. So you'll have to pick up from context whether you're talking about degree K or K degree to figure out which of these two you want to use. So let's just work a couple examples real quick. Let's take 90 kelvins and convert it to degrees C. Now, when I look at this, I don't have a degree sign in front or in back, so I don't know if this is a reading or a difference. But then, since the question asked to convert it to a temperature reading, this would only make sense if this were also a reading. So we'll use the reading conversion relation. So TK equals TC plus 273.15. So a Celsius reading would be the Kelvin reading minus 273.15. So this will be 90 minus 273.15 is negative 183.15 degrees C. And as another example here, let's go and convert 50 C degrees to Kelvin. Again, because there's no degree sign here in front or in back of the K, here I'll have to go look over here and see, oh, there's a degree sign after the C. So this is a difference. So if we are converting temperature differences, this is going to be delta TK equals delta TC. So it's just 50. So there you go. Alrighty. So there is one, actually two footnotes that I want to make to this. This is not what I just gave you just now, is not the current official definition. In fact, it wasn't even the prior official definition of Kelvin. In the prior official definition of Kelvin, the lower reference point was indeed absolute zero. But the upper reference point was actually 273.16 Kelvin instead of 15. And this is because water has a special property that at a rather low pressure, 611.73 pascals, and by comparison, atmospheric pressure is 101,300 pascals. So we're talking pretty darn low pressure here. More on that when we do pressure officially. It turns out that at this temperature, 273.16, at this ridiculously low pressure, the solid, liquid, and gas phases of water will simultaneously coexist. It's called the triple point of water. And since it can only happen at one exact temperature and one exact pressure, it's a very precise way to calibrate a scale. And so the official definition was actually built around this triple point, which was 1/100th of a Kelvin higher than the freezing point of water at atmospheric pressure. Now, under the latest and greatest definition, when the definitions changed in 2019, the lower, now the doing it this way of defining it using an upper and lower scale has been replaced with something completely different. It's actually now tied to the average kinetic energy of the molecules under study. In a few video series, we will get to that. All right. So but however, the triple point of water still remains as a practical measure. Alrighty. So in the next video, we will start to dive into the laws of thermodynamics. Catch you on the flip side.